Hi everyone, welcome to the session on model and data parallelism with Amazon SageMaker. We'll talk today about accelerating natural language processing training with Amazon SageMaker. My name is Aditya Bindal, and I'm a senior product manager with AWS. We'll start by talking about Hugging Face and how our customers train NLP models on Amazon SageMaker. We'll talk about some of the challenges in training these NLP models, and then we'll see how SageMaker's distributed training libraries solve these problems for customers. We'll see some benchmarks on performance with state-of-the-art models, and finally, we'll walk through some examples on how to use these new capabilities with PyTorch and with TensorFlow. So let's talk about using Hugging Face on Amazon SageMaker. NLP has grown rapidly in the last few years. We now have state-of-the-art models hitting human baselines in several common language tasks. Our customers can find highly accurate pre-trained models in reference architectures for machine translation, for question and answering, for text generation, and several other NLP domains. And we have a lot of customers building NLP solutions on AWS today. For example, Grammarly offers writing assistance through a combination of natural language processing and advanced machine learning, including training in Amazon SageMaker. Novartis uses the state-of-the-art BERT NLP model in Amazon SageMaker to enrich a knowledge graph. And so we work closely with our friends at Hugging Face to make it even easier for customers to use natural language processing on AWS. Now, Hugging Face is one of the most popular open source libraries and frameworks for natural language processing, and AWS has a fully managed end-to-end platform for training and deploying machine learning models in Amazon SageMaker. So let's talk a little bit about the Hugging Face libraries, specifically the datasets, tokenizers, and transformers library. It is a very popular open source repository. It has over 58,000 GitHub stars as of May 2021 and over 1 million downloads per month. It offers different Python NLP specific front ends for both TensorFlow and for PyTorch. And it provides state-of-the-art transformer-based models that you can use to fine-tune with your own datasets or deploy directly for inference with the pre-trained checkpoints and weights. On top of that, it has a comprehensive model zoo with over 7,000 different models in over 160 languages. So what we recently announced with Hugging Face jointly was a new experience for using Hugging Face on SageMaker. And there are a few key components that make up this new experience. We created new deep learning containers co-developed with Hugging Face, and they integrate all of the Hugging Face libraries and models with SageMaker features such as the debugger and the distributed training libraries. We also created a brand new estimator in the SageMaker Python SDK that customers can use to create training jobs using the Hugging Face libraries and models. And then we created an example gallery that's continuously growing to find high quality samples of Hugging Face training and fine-tuning scripts on SageMaker. And all of this is supported and maintained by AWS, giving you the same level of SLA, documentation, examples that you would get with any other feature in Amazon SageMaker. Now, what are the benefits of using Hugging Face in Amazon SageMaker? Well, the first point is that it's cost effective. SageMaker optimizes the performance of your models and does all the heavy lifting of provisioning compute servers, configuring them correctly with exactly the right stack of underlying accelerator libraries, drivers, machine learning frameworks, and other optimizations that will help you reduce your training time and training cost. We also provide managed spot training that lets you leverage EC2 spot instances to reduce your training costs even further. The solution is MLOps ready. It includes all of the tooling that SageMaker provides for full CI/CD and traceability in your entire machine learning workflow. It's scalable. We've designed this to allow you to run training and fine-tuning jobs on a cluster of GPU instances. And this leverages our recently launched data parallelism and model parallelism libraries that allow you to train state-of-the-art training models within hours that used to previously take days or weeks. And we have a high bar in security. So all of the available mechanisms, such as encryption at rest and in transit, VPC connectivity, and fine-grained IAM permissions, are fully integrated with this Hugging Face on SageMaker experience. Now, the workflow that you see and what customers are using today to use Hugging Face with SageMaker spans the full cycle of building, training, and deploying your machine learning models. So here you can see how a customer may develop that training script on a SageMaker Studio instance or on an IDE, and then they create training jobs on SageMaker Training using the new Hugging Face deep learning containers and the Python SDK estimator. All of those deep learning containers and training environments have integrations like the SageMaker training libraries for distributed training, as well as the debugger and the profiler. And then using that model artifact in Checkpoint, you can create an endpoint and deploy in SageMaker hosting. So let's dive into training specifically. You write your training and fine-tuning script in SageMaker Studio or an IDE of your choice, and you launch the job with the estimator. The job runs in SageMaker Training, which provisions the underlying compute infrastructure, and then saves the checkpoints and model artifacts in S3 and outputs the logs in CloudWatch. So going a little bit deeper, let's see how this looks from an example with PyTorch. So in this example, we picked the Distilabert based uncased model from the Hugging Face repository, and we select that model in the hyperparameters argument. We then use the new Hugging Face estimator in SageMaker's Python SDK. We specify the training script, the compute cluster, the framework and library versions, and we pass those hyperparameters. And then we call fit to begin training our model on that stack. And then here's the same example, but with TensorFlow. So you'll notice everything is exactly the same. I'm using my hyperparameters to use the Distilabase BERT uncased model, and I'm now calling the TensorFlow estimator and specifying TensorFlow version instead of PyTorch version. And so we have many more examples. It's an ever-growing list of sample notebooks and documentation you'll find on AWS, as well as on Hugging Face. There are some links here to get started with examples in TensorFlow and PyTorch with distributed training, single node training, training with custom metrics, training with Spot instances. And I want to highlight a few customers that are using Hugging Face and SageMaker today. So Quantum Health trains NLP models to help agents and their members. They use Hugging Face and SageMaker's distributed training libraries to reduce the training time for their larger datasets. Customer is a CRM platform, and they use NLP to contextualize conversations. They plan on using Hugging Face on SageMaker to fine-tune models for text classification and semantic search. MusicMax helps users share and search song lyrics with translations, and they're looking forward to using transformers in SageMaker to train state-of-the-art language models. Now let's talk about some of the challenges in training state-of-the-art NLP models. These are really the next level of issues that customers would hit when they try and train some of the latest and greatest and most accurate NLP models. So customers have told us that training these state-of-the-art models can take a very long time. Even on compute clusters with hundreds or thousands of GPUs, training can take several days. And this prevents data scientists from iterating and getting that trained model into production faster. Now, we know scaling to more GPUs can reduce training time, but how do we think about the costs and the benefits of training a model in multiple GPU instances? So let's talk about scaling efficiency and define it. In an ideal case, if it takes you 8 hours to train with one instance or one node, it should take you 1 hour to train with 8 nodes. So your cost remains the same, but your time to train drops. In practice, you don't scale perfectly, and we'll talk in a few minutes about why that's the case. And we can define and measure weak scaling efficiency as a percentage of the ideal linear scaling efficiency that you could get. So if ideal scaling efficiency is 100%, you may see a scaling efficiency of 90%, for example, where your training time would decrease by 86%, but your cost would only increase by 11%. When your scaling efficiency is high, you have no trade-off between the time to train and the cost to train. When the scaling efficiency is low, you have a trade-off to make, and you're not able to utilize the compute infrastructure efficiently. So let's do a quick recap of how data parallelism works. The core idea is that you parallelize training by giving each GPU a replica of the model and a subset of the training data. So here in this diagram, we have four GPUs, each with a copy of this four-layer neural network model. And each GPU gets different mini batches of my training data. But now that each GPU is training the model in a different slice of data, we need some way to reconcile and get a single model back again. So we need to synchronize gradients across these machines. We need to communicate the gradients between different servers. So there are two core approaches here. Parameter servers were the dominant way of synchronizing gradients. Worker nodes would pull the model from parameter servers, train with their mini batch, and then push their version of the model back up. Then the parameter server would average the gradients and make an updated model available to all workers, and you would repeat this process again. But this resulted in an imbalance in the amount of data that was being sent and received from each server that caused bottlenecks and slowed training down. It also made the system less stable when you increased the size of the cluster and had hundreds of thousands of GPUs. The other and more dominant paradigm today is using communication primitives like allreduce. So borrowing from the HPC community, we used MPI methods to accumulate gradients by letting GPU instances communicate directly, typically in a ring or a hierarchical topology. So this addressed the latency and the stability challenge of parameter servers, but it still didn't efficiently utilize the bandwidth in AWS. And we challenged our teams to come up with a better way to do gradient synchronization at scale on the infrastructure and network and topology that you find in Amazon Web Services. And we came up with a solution that takes the best of both worlds, and we'll talk about that just in a minute. So let's go back to why scaling efficiency tends to be low. It's often because the network becomes a bottleneck. So when you have typically four components in your training loop, forward pass, backward pass, allreduce step, and an optimize step, as you add more machines to your cluster, this allreduce or gradient synchronization takes longer and longer until it becomes your bottleneck. So even though you're adding more GPUs to your compute cluster, you're not able to utilize them efficiently because you're spending so much on this network communication overhead. And with prior solutions, we found that as you added more and more GPUs to your cluster, you weren't getting the benefit from additional compute, and your GPUs were underutilized. So your scaling efficiency would drop to somewhere around 50 to 60% when you kept adding more and more GPUs to your cluster. Now, let's talk a little bit about deep learning models in the NLP space that have been growing in size. So we see a trend where every year, less than maybe every 10 months, we see models increasing in size by almost 10x. We saw BERT in 2018 that had 340 million parameters, and then GPT-3 most recently had 175 billion parameters. And the reason for this trend is that larger models are improving accuracy. They're also allowing us in some specific cases and domains to do 0-1 few-shot learning during inference, which saves us from the time and cost of preparing a large labeled data set and fine-tuning it. One large model can then be reused several times in different domains with little or no fine-tuning. We also see hardware improve, but the model size tends to be outpacing the growth in GPU memory. And the result of this is that memory becomes a bottleneck during training. So the model size is limited by the memory of a single GPU, and it produces out-of-memory errors. Replicating the entire model across GPUs is then also wasteful when the model is large. So the solution to this problem is model parallelism. You partition the model replica across GPUs instead of in data parallelism where you have the entire model replica in each of the GPUs. But model parallelism is hard to implement. It requires a lot of hand tuning for performance. Existing solutions are tied to very specific implementations of a few transformer models, and they often require rewriting your entire training script with custom operators and code. There's no general framework today for automatically and efficiently partitioning any model across GPUs in any domain. So these were the problems that we set out to solve, and let me now talk a little bit about the main features of SageMaker's distributed training libraries that were launched recently at reInvent. So stepping back, we have teams within Amazon that have been solving these types of problems at this scale internally for quite some time. And for 3 years in a row since 2018, we've demonstrated the fastest training time on record for popular models like T5, BERT, Mask RCNN, and ResNet. Last year, we published some of the science behind these results at SC20 in a paper titled Herring, Rethinking the Parameter Server at Scale for the Cloud. And now we've made all of this available to developers through Amazon SageMaker with an easy-to-use API. We created two libraries called smdistributed.dataparallel and smdistributed.modelparallel. And these libraries solve all the challenges with network and memory bottlenecks that we talked about. And they require no tuning for high performance, and they provide a general framework for data parallelism and model parallelism in both TensorFlow and PyTorch. So let's start with the data parallel library. It's designed to reduce training times for distributed workloads that are network bound. It's built from the ground up to fully utilize AWS infrastructure and topology, leveraging the point-to-point communication we have between EC2 instances using the Elastic Fabric Adapter, or EFA. We find that it's consistently 20 to 40% faster and cheaper in training time and training cost across different models, domains, and frameworks than the prior alternatives. So how does it work under the hood? Well, when you launch a training job with SageMaker Data Parallel, the CPUs on your GPU instances become parameter servers. We introduce a new technique called Balanced Fusion Buffer to make optimal use of bandwidth. A buffer in the GPU holds gradients until they hit a threshold size. We then copy the fused buffer to CPU memory, shard it into n parts for each node in our cluster, and then we send the ith part to the ith server. This balances the data being sent and received from each parameter server, ensuring bandwidth is efficiently utilized and addressing the primary challenge with traditional parameter servers that we talked about a few minutes ago. Now, because we designed this all-reduce algorithm for AWS infrastructure and topology, it's also more stable and fault-tolerant. Another benefit is that we offload all-reduce from GPUs to CPUs, which then allows us to overlap the backward pass and the all-reduce operation, which lowers the overall step time and frees up GPU resources. So architecturally, there's no change in how you use SageMaker to train models when you use this new data parallelism library. Your training data live in S3, you create a training job using the SageMaker Python SDK, and when the job completes, you have a saved model artifact in your S3 bucket. Now let's look at the model parallel library. It's automatically and efficiently partitioning your model. It's setting up an efficient pipeline that maximizes GPU utilization, and all of this takes place in a fully managed environment in SageMaker that's integrated at the framework level with TensorFlow and with PyTorch. So let's see how this works. When you create a training job, SageMaker analyzes the model graph, including analyzing tensors using SageMaker Debugger. SageMaker then partitions the graph in a way that balances compute and minimizes communication. Finally, it sets up an efficient pipeline to execute mini batches. Now, SageMaker splits each batch into smaller micro batches, and these micro batches are then fed sequentially as the animation shows. So we overlap the forward and the backward pass for these micro batches to maximize the amount of time GPUs are running and doing their operations instead of being idle and waiting for data of a complete batch to arrive. And just like the data parallel library, there's no change to how you set up and run your training jobs in SageMaker. So let's look at how these libraries perform today. With the T5 3 billion model, we set record training times last December at reInvent using this new SM distributed library. We trained this model in just over 4 days on 256 P4D 24x large instances, which is 2048 A100 GPUs. And with the data parallel library, we were able to speed up training on Roberta by around 32%. And we also showcased record results with MOSC CNN at reInvent in December 2020. So we're continuously working on performance, and we have more optimizations planned this year. So let's walk through an example of using the data parallel library with PyTorch. So before we saw how you can use the new estimator functions with the Hugging Face and SageMaker integration to create training jobs. Now we're going to look at the actual training script and look at how you can leverage these new libraries and call these APIs directly. So we start by importing the SM distributed library and initializing it. If you use PyTorch Distributed Data Parallel or DDP, this should look identical and intuitive to you. No changes are required to your model definition, the core training loop, or evaluation. Nothing needs to change here. And now what we do is we replace DDP with SageMaker's data parallel library. So we scale the batch size by the number of processes. We set the number of replicas equal to the number of workers, and we set the node rank. We wrap the model with our version of DDP, and we pin each GPU to a single SageMaker data parallel process. Finally, we save checkpoints only on the leader node. And if you've used DDP, this should all look very familiar and identical to what you would do today with DDP. And that's it. We've made all the training code changes that we need to, and we're ready to train our model and enjoy all the performance and stability benefits that we've talked about. Now let's walk through an example with the model parallel library, and we'll use TensorFlow for this one. So let's modify this TensorFlow training script. And the first thing we'll do again is we will import and initialize the SM distributed model parallel library. And we'll switch from the keras.model to our distributed model. And this is how all operations within the model class will get partitioned automatically. So anything that you want to place on every single GPU device and not partition, you would put outside this class definition. We then extract the forward and the backward passes into a decorator function, like shown below. And this feeds into the training step. And the output tensors are then averaged across the micro batches to get a single tensor. So remember, with the pipeline we set up, we overlap the forward and the backward by splitting up into these micro batches and creating an interleave pipeline. And now we would average across these micro batches to get a single tensor. And you can also define your own model partitions and override the automated partitioning. So some customers may want to start by using the automated partitioning algorithm and then switch to a manual override if they want to make tweaks based on performance, accuracy, or any other requirements. And finally, you can directly call Horovod to use a hybrid of data and model parallelism. If we were doing this in PyTorch, you could directly call distributed data parallel or DDP to use a hybrid of data and model parallelism. SageMaker's model parallelism library will automatically implement the data parallelism and the model parallelism for you. And we made this available to all developers through Amazon SageMaker with framework level APIs. So to summarize, these are two new libraries, smdistributed.dataparallel and smdistributed.modelparallel. They support both TensorFlow and PyTorch, and one solves for the network bottlenecks, that's SageMaker distributed data parallel, and the second solves for memory bottleneck, that's SM distributed model parallel. And they require no tuning for high performance. They support multiple domains, frameworks, and model architectures, and require minimal code change in your training script. If you'd like to learn more about machine learning in AWS, I encourage you to check out some of the links in this slide, including the URL aws.training/machine learning. Thank you so much for your time. I hope you found this session useful. There's a survey at the end. Please complete the session survey. Thank you.